Hello everyone, this is the first class on computer architecture, so I'd like to take this opportunity to welcome everyone and give you some information about what you're about to learn in this series of lectures in the coming weeks. This class considers and teaches computer organization, different parts of a computer that makes it run and talk to other devices around it. This discussion involves the details of a generic CPU design instruction set architecture, which is the interface between the hardware and software, the I/O devices, memory, and other advanced topics which made our modern processors run fast. Current trends like multi-core architectures, vector instructions for fully utilizing the available parallelism in hardware, pipelining, for example. These topics will also be covered towards the end of this class, and I hope you enjoy the show. So let's start with the basic question, why do we learn about computer architecture? Well, first of all, to be able to say where the computers are headed, right? So this involves predicting the future trends of computer technology, novel capabilities which may appear in different form factors, new and branching applications in every engineering discipline you can imagine. Secondly, to be able to understand all level design concepts. That's to say, from the very low digital circuit level to the right top of the programming stack, where you can write applications with little, if not no information about the hardware. And to be able to compare computer performances. So compare computer performances can, for example, help you in daily lives when you want to buy a laptop or a desktop computer. And another reason to be is to be able to write better software. Knowing the hardware ultimately enables you to write efficient and fast software for it. Of course, this is based on the assumption that underlying architecture exposes most of the capabilities of hardware to the software level. And most of the so we'll learn more about this. And the final reason is to be able to design hardware. And most of the giant companies have their own hardware design team. So learning about computer architecture can help you become a good hardware design engineer. So let's start with the computer architecture's definition. There are two definitions. The most conventional definition is the science and art of designing, picking, and interconnecting hardware components and establishing the hardware-software interface to create a computing system that meets functional performance, energy, power, cost, and other specific goals. There's also another definition given by the famous computer scientist Amdahl in April 1964, and that definition is the term architecture is used to describe the attributes of a system as seen by the programmer, and we'll basically dwell on the system as seen by the programmer at the end of this class. In other words, the conceptual structure and functional behavior is distinct from the organization of the data flow and controls, and the logic design and the physical implementation of that logic design. The main goal of this course is to learn and think about the machine from an architectural level. A top-down approach would entail learning about high-level as well as the assembly level and finally logic-level languages to control the hardware. And different levels of abstraction, which we will discuss in a bit, constitutes the basis of a computer design. So one of the other goals of this course is to understand the relationships between these levels of abstraction. And hopefully by the end of this course, you will be able to recognize computer components, know more about the processor design, memory, cache hierarchies, I/O devices, storage subsystems, and a large set of trade-off space in which you can achieve a particular design point. And eventually my role would be to push you to learn something new. And after establishing the background, hopefully we'll explore the newest trends together. So let's look at the contents of this class. We'll mainly focus on the computer organization and learn more about the general purpose CPUs, processors that can do anything. That's what the meaning is when we talk about general purpose. For example, running a full operating system. Examples include Intel Core i7, AMD Athlon, IBM PowerPC, ARM, or Intel Itanium. Computers. There are also application-specific CPUs like ASICs, application-specific integrated circuits. They can do video coding, 3D rendering, imaging. So the one notice that to make is that hardware is less flexible but more parallel than software, and hardware is faster and most of the time is less costly. Learn about. We also want to the contents also includes the learning about micro architectures and instruction set architecture. It involves the learning about memory, caching I/O, and learning about pipelining, multi-core architectures, multi-threading, branch prediction if time allows. Let us start with the fundamentals. Let's take a look at the Moore's law and remember what Moore's law is. So it was about adding more transistor. Gordon Moore, the CEO of Intel, has said maybe 40, 50 years ago, by adding more transistors to the CPUs, we can make them work faster. So this is also the name called transistor miniaturization, and it's about doubling the number of transistors every 18 months. When we look at the microprocessor history and the revolutions that happened in the history, one significant technology the threshold was crossed in 1970s, because it was the time where enough number of transistors are put together to design a 16-bit processors on one single chip. With this development, microprocessors have allowed new market segments. For example, desktops, computers, CD, DVD players, laptops, game consoles, set-top boxes, mobile phones, digital camera, MP3 players, GPS, automotive electronics. So microprocessor-based system basically replaced all supercomputers. Then the second revolution followed that, and it's the implicit instruction level parallelism. Hardware now provides parallel resources, and new techniques in that time frame allowed us to learn how to use them. Software by the way, is oblivious to these changes in the hardware because it's not exposed, and it basically started initially using some technique called piplining, which also enabled increased clock frequency. And then it followed the caches, which become necessary as processor clock frequency increased, and the integration of floating point unit also followed that set of sequence of advancements. Then deeper pipelines, branch speculation, the multiple instruction per cycle like superscalar technology appeared, and finally dynamic scheduling, out of order execution. And these advancements were applicable to single core. Then processors, start to support explicit data thread level parallelism. And hardware provided, parallel resources again. Software specifies now usage for these parallel resources. So why software is involved? Because on instruction level parallelism has shown diminishing returns in the past. And then, people now wondered about if software can be involved in that process. And this progress involved vector instructions. For example, Intel's SSC instructions, and one instruction does, for example, 4 parallel multiplications or additions. And also, these processors had the general support for multi-threaded programs. First with single core multi-threading, and then multi-core multi-threading. And now when we look at around, we can see that there are a lot of other techniques like GPUs with thousands of cores and capable of running multiple tasks at the same time. So that's where the trend is going. So to give you some examples from the past for the 3 revolutionary points of history, let's consider one of the dominant key players of the microprocessor market today, Intel. Intel Corporation's 1971 4-bit microprocessor, that's as shown in this slide. It was named 4004, and with the limited capabilities, this microprocessor was used in calculators. And you can also see the set of specifications of hardware in this slide. When we reached the 2003, Intel's Pentium 4 has been released. This product was to serve the desktop as well as server level needs, speeds reaching up to 3.4 gigahertz. It was the maximum frequency a single core has reached at the time. This was possible mainly due to 55 million transistors and advanced technologies such as deep pipelining and superscalar technology enablers, caching, etc. This process was kind of Intel's last and best effort for single-core microprocessor era, because after that the third revolution has happened and microarchitectures become predominantly multi-core. The details of this processor is summarized in this slide. When we reached the 2013, a great example to the final revolution of microprocessor has happened. And Intel, released their product called Core i7, and this was intended for desktop and server computers as well. The main difference of this piece of hardware was the multi-cores staying on the same die, and 55 million transistors had now climbed up 30x, compared to the previous generation Pentium 4. Each core's frequency has stayed the same, and advanced caching is allowed, while the legacy Pentium 4 capabilities are all included in different flavors into these products, making them one of the best processors in the market. So with each core can run 2 threads in parallel. The microprocessor, that technology is called, by the way, hyperthreading. The process can run now 8 threads all in parallel. So that's a huge improvement from the previous generation of CPUs. So as you can see, as what we watched the revolutionary steps of computer CPU, the overall system is becoming more complex with each generation. So the question is, how do we really deal with such a complex system? The answer is abstraction and layering. Abstraction involves dividing the world of jobs into objects and each having their own interface. And one module does not know what the other is doing really. So it's like a black box to them. Only specialists deal with the implementation and the rest of us with the interface. Secondly, layering is key. However, layering is nothing but repeated abstraction. It's about dividing the objects of the system into smaller but simpler layers so that a given layer does not need to know what the other layers are doing, but just the interfaces. However, there are disadvantages associated with abstraction and layering. For example, layer and abstract and modules interfaces become entrenched over time. In other words, once they become part of the standards, it's very difficult to change, even if the benefit is clear. Another disadvantage is that layering and abstraction make it hard to reason and predict about the performance across layers. So how do we really make electronic circuits solve our problems using this kind of abstraction and layering? Well, through the abstraction and layering, the ideas are suggested from the previous slide. A complex computing machine can be designed through something called stack. The complete stack is summarized for you on the right. The top of the stack has the problem layer, which involves the literal definition of the problem. Then the algorithm is designed to solve that problem. A program is written next using one of the high-level languages, such as C and Java. This language goes through a process called compilation, and the runtime environment allocates the resources for this program to be translated using the hardware-software layer language known as the ISA, the instruction set architecture, and then with the ISA, one can talk to the underlying microarchitecture. The microarchitecture is nothing but a particular set of complex combination of logic circuits which can serve a specific set of purposes. And finally, digital logic circuits consist of gates which are made of electronic components and circuits help you execute those instructions. This course is about ISA, microarchitecture, and some digital logic. I also have summarized some of the classes you'll take in MEF University to complete the learning process about these stacks. Let us refresh our memories and remember the basic building blocks of a computer. The basic computer consists of 3 main elements actually: memory, CPU, and input-output. So CPU was the brains of the computer where the computation takes place, whereas the memory was used to store data for later use. I/O was the interface to outside, which included network devices, keyboard, mouse, monitor, and printers, etc. The CPU has 2 units called data path and control. CPU is connected to memory and I/O devices as shown in this picture, and the connections are established through communication links and protocols. So if we look at the computer from a programmer's perspective instead, we can draw a picture as shown in this slide. In this example, we'll assume that we use GCC software compatible operating system, and we start with the high-level language programming as usual. This could be written in C, Java, or Python. So let us say our source code is in a file hello.c. The first step to the process is the pre-processing. In this stage, texts are substituted, comments are stripped, appropriate addresses are replaced with full locations for file inclusions. The pre-processing produces the output file hello.i. So this file also includes all macros expanded appropriately. So it's ready for compilation. Next, compilation takes place and produces the appropriate assembly language instructions in a file called hello.s. Of course, to be able to do that, compiler needs to know the underlying ISA, the architecture. Otherwise, it will not be able to generate the right set of instructions, right? The assembler next takes a role, and it's nothing but a translator, the language translator. It translates the hello.s to hello.o, the object file, which has the corresponding binary and machine code of the assembly instructions. If the source code has procedure calls to other functions from other C runtime libraries, the assembler leaves those particular places blank, and these places are going to be filled in by the linker using other object files. The completed object file called the hello.out is now executable and loaded in proper memory location for the instruction fetch cycle to take over and execute the instructions. Alright, so in this class we briefly introduced computer architecture basics, the programming point of view, and motivated you for the next lecture, hopefully. So we have also mentioned about important topics such as abstraction and layering. All these concepts mentioned in this class will be explored in detail later in the course, but these are to have you start thinking about it and investigating and learning more about these concepts and particularly what they mean. In the next lecture, we'll explore cost and performance fundamentals so that we can compare computers. We'll also talk about energy, power, most critically reliability aspects of computer systems. So a lot of excitement and adventure waiting for us. Just stay tuned. Needless to say, please feel free to drop any questions you might have about today's lecture into my email box, and I'll be more than happy to help you with your questions. Thank you very much.